I want you to take a second and just imagine a scenario. It's the climax of Carl Sagan's classic sci-fi novel, Contact.
Oh, right, the 1985 book.
Yeah, exactly. So humanity has been searching the cosmos for extraterrestrial life, pointing these massive radio dishes at distant stars. But the ultimate discovery doesn't actually come from a telescope.
Right, it comes from a computer crunching numbers.
Exactly. Deep inside the digits of pi, that infinite mathematical constant we all learned about in geometry, class scientists discover a hidden message.
Which is just a brilliant concept.
It really is. It's a sequence of zeros and ones that perfectly forms the shape of a circle, like an intentional signature, just buried in the very fabric of the universe.
Yeah, and it remains one of the most, I think, compelling thought experiments in modern science fiction. The idea that mathematics itself, like the underlying code of reality, could hold a deliberate message just waiting for us to find it.
But what if this wasn't just science fiction? Like, what if finding a message in pi was an actual mathematical possibility?
Well, that's what we're getting into today.
Right. Today, we are taking a deep dive into the heavy, mind-bending math that asks a very real, very profound question. If we actually found a code in the cosmos, how could we prove it wasn't just a random, meaningless coincidence?
Which is honestly a massive epistemological hurdle. I mean, we aren't just talking about cool math facts today. We are exploring the entire philosophy of pattern discovery.
How do we uncover truth, basically?
Exactly. How do we know when a pattern is a genuine signal of design, and not just our human brains playing tricks on us by connecting random dots?
So our mission today is to shortcut the heavy academic jargon in our source material and give you a mind-expanding aha moment about how we actually observe the universe.
It's going to be a fun one.
So let's unpack this. Why is finding a message in pi mathematically problematic in the first place? I mean, if I find a circle made of ones and zeros, shouldn't that be proof enough?
No. Because to understand the problem, we have to talk about a concept called the Texas sharpshooter fallacy.
Okay, the Texas sharpshooter. Let's hear it.
So imagine a guy with a gun. He walks up to the side of a massive blank wooden barn, closes his eyes, and just unloads his weapon, firing shots completely at random all over the broadside of the structure.
Sounds incredibly reckless, but I'm tracking with you.
Right, well, after he's done shooting, he walks up to the barn and inspects the damage. Naturally, purely by chance, there happens to be a cluster of 3 or 4 bullet holes that are really close together.
Just statistically speaking.
Exactly. So he takes out a paintbrush, and he paints a bullseye right around that specific cluster.
Uh,
Then he steps back, calls his friends over, and says, "Look, I'm a sharpshooter."
oh, I see. He painted the target after he took the shot.
Yes.
He's claiming he had intentional accuracy when in reality he just engaged in post hoc pattern selection. Like he let randomness do the work and then assigned meaning to it after the fact.
And that is the exact objection skeptics raise against the contact scenario. The digits of pi, 3.14159 and so on forever, they are presumed to be infinite.
Right.
And they are also presumed to be what mathematicians call normal. In a normal number, the digits are evenly distributed, meaning literally every possible finite sequence of numbers appears somewhere if you look long enough.
Wow. Okay. So, I mean, it's like staring at clouds.
Yeah, that's a good way to put it.
If you lie on the grass and look up at a cloudy sky for a few hours, eventually you are going to see a cloud shaped exactly like a dog. But that doesn't mean the cloud was intentionally designed to be a dog.
Exactly. The atmosphere didn't sculpt a golden retriever just for you.
Right. It's just a random chaotic shape that your human brain assigned meaning to after the fact. So, if I have a supercomputer, I could search trillions upon trillions of digits of pi and eventually find my birth date. Or a circle of zeros and ones, or even the binary code for an entire Shakespearean sonnet.
Yes. And if you find Shakespeare at the trillionth digit, the skeptic will just say, well, you didn't specify where to look beforehand. You just scanned an infinite data set until you found something neat, and then you painted the bullseye around it.
You're just being a Texas sharpshooter.
Precisely. Without predicting the pattern's location or its exact nature before you started searching, you have proved absolutely nothing.
So what does this all mean then? If finding a pattern doesn't actually prove anything, how can we ever prove a message is real without just magically guessing what it is and where it is beforehand?
Which is the big question. And the answer requires a complete shift in our thinking. The source text argues that the solution isn't about what we find. It is entirely about how we access it.
How we access it. Okay.
Yeah, and to understand that, we have to go back to a revolution in mathematics that happened in 1995.
1995. Good year. We had the launch of the DVD, the original PlayStation, and apparently two mathematical tools that completely changed the game for how we look at pi.
They really did. In 1995, two fundamentally different approaches to computing pi were discovered. But to appreciate the first one, you have to understand how brutal computing pi used to be.
Oh, I can imagine.
Historically, if you wanted to know the millionth digit of pi, you were forced to calculate the 999,999 digits that came before it. You had to compute it sequentially, carrying the remainder over and over again.
Because it's a sequence. You can't know step 10 without finishing step 9.
That was the assumption.
Yeah.
But the first tool discovered in 1995, called the BBP formula, named after its creators Bailey, Borwein, and Plaufi, it shattered that limitation completely.
How so?
It allows you to extract the nth hexadecimal or base 16 digit of pi directly, without calculating any of the preceding digits.
Wait, hold on. How is that even mechanically possible? How do you just skip the line like this?
It's crazy, right? It uses a brilliant property of modular arithmetic.
Okay, you're going to have to break that down for me.
Sure. Think of modular arithmetic like math on the face of a clock. If it's 10 o'clock and you add 4 hours, it doesn't become 14 o'clock, right? It wraps around back to 2 o'clock.
Right, because you only care about the remainder.
Exactly. So the BBP formula uses a specific polynomial equation that basically treats the infinite string of pi like a giant clock. It divides the math in such a way that it isolates a single specific digit position by discarding everything before it as a neat, wrapped-around remainder.
Oh, wow. Okay. So if the old way of calculating pi was like a one-way conveyor belt where you have to stand there and watch every single item roll past until you spot the one you want.
Which would take forever.
Right. Then the BBP formula is like having a GPS coordinate system. Or honestly, like a teleporter.
Teleporter. I like
Yeah. You can punch in digit 1 trillion, instantly beam down to that exact spot, grab the number, and beam back.
that teleporter analogy hits the nail on the head. You bypass the sequence entirely. But 1995 also gave us a second tool, and it perfectly represents your conveyor belt idea.
Oh, really? What's that one?
It's called the Rabinowitz-Wagon spigot algorithm. And unlike BBP, the spigot algorithm does not let you skip ahead. It produces base 10 digits, our standard everyday decimal numbers, sequentially.
So like a dripping spigot.
Exactly. Drip, drip, drip. You are forced to compute them in order. It mechanically processes a classic mathematical series, and as it churns, it spits out the digits of pi one by one, natively in base 10. You cannot fast forward.
Okay, here's where it gets really interesting for me. I see an aha moment forming here.
Oh, yeah?
Yeah. If I use that conveyor belt, the spigot algorithm, to find a pattern, I'm just scanning. Like, I could watch the belt for 10 years, stop at a random point and say, look, I found Shakespeare.
Which brings us right back to the Texas sharpshooter fallacy.
Exactly. I scan until I found something cool.
Yeah.
But BBP changes the game completely. Because it's a teleporter, it allows for testable predictions.
Yes.
I don't have to scan endlessly. I can say, I hypothesize there is a message at hexadecimal address 10 to the 15th power, and then I can just teleport there and check.
Spot on. You aren't painting the target after the shot anymore. The BBP formula gives you the exact coordinates before you shoot. And what's fascinating here is that the author of our source text argues these tools aren't just fancy calculators. They function as literal mathematical observatories.
Mathematical observatories. Like a telescope, but for numbers instead of stars.
Exactly. In astronomy, the physical structure of your telescope dictates what kind of light you can see. A radio telescope reveals a completely different universe than an optical telescope.
That makes sense.
In mathematics, the instrument of discovery actually creates the conditions for the pattern to be visible. To prove this isn't just an abstract theory, the source material walks us through some historical mathematical miracles.
Miracles. That's a strong word for math.
Well, these are moments where, changing the mathematical lens, the observatory revealed undeniable, shocking structures that were completely invisible before.
Okay, if BBP gives us a new lens to see pi, I want to know if changing lenses has actually revealed something hidden in the past. Walk me through one of these miracles.
All right, let's start with the Ulam spiral from 1963. The mathematician Stanislaw Ulam was stuck in an incredibly boring presentation.
We've all been there.
Right. So to pass the time, he started doodling numbers on a piece of grid paper. He wrote the number 1 in the center, and then wrote 2, 3, 4, spiraling outward in a square shape, wrapping around and around indefinitely.
Just a standard Archimedean spiral of integers.
Yep. But then he decided to circle all the prime numbers, numbers like 3, 5, 7, 11, which can only be divided by 1 in themselves.
Okay, simple enough.
Now, on a standard straight number line, Primes are notoriously unpredictable. They look like random static. But when Ulam plotted them on this two-dimensional spiral, something incredible happened. The primes started heavily clustering along diagonal lines.
Wait, random static suddenly formed straight lines just because he bent the number line into a spiral?
Yes, the geometry of this spiral coordinate system actually forced these diagonal lines to appear, and those lines mathematically corresponded to prime-rich quadratic polynomials.
Okay, stop right there. Prime-rich quadratic polynomials. They're going to have to explain that like I'm 5.
Fair enough.
Okay.
Let's take Euler's famous formula, n squared plus n plus 41. If you plug in a whole number for n, let's say 1, 2, or 3, and do the math, the answer that pops out is almost always a prime number.
Oh, so it's an equation that practically manufactures primes.
Exactly. And what Ulam's spiral did was take equations exactly like that one and physically manifest them as diagonal visible lines of ink on the paper.
So the structure, like the hidden machinery of the primes, was always there, but it was completely invisible to the human eye until he used a spiral as his observatory.
Precisely. And that concept scales up to even more unbelievable discoveries.
More unbelievable than that.
Oh, yeah. Take the Montgomery-Dyson connection of 1972. Hugh Montgomery was a mathematician studying the Riemann zeta function. Simply put, he was looking at the incredibly complex gaps between prime numbers. He found a specific statistical pattern governing how those prime gaps are distributed. And by pure serendipity, he stopped for afternoon tea at the Institute for Advanced Study and casually mentioned his prime number equation to a physicist named Freeman Dyson.
Oh, boy. I feel a collision of two completely different worlds coming on.
You're not wrong. Dyson took one look at Montgomery's equation for prime numbers and instantly recognized it. It was the exact identical mathematical structure to the random matrix eigenvalues used to describe the energy levels of heavy nuclei in quantum physics.
Whoa, hold on. Random matrix eigenvalues. You lost me. What does quantum nuclear physics, like the literal behavior of uranium atoms, have to do with the spaces between prime numbers on a chalkboard?
Absolutely nothing, or at least they shouldn't have anything to do with each other. One is pure abstract number theory. The other is messy real-world subatomic physics.
But the math matched.
Perfectly. The statistical spacing between the energy levels of a heavy nucleus matched the statistical spacing of prime numbers perfectly. It's like finding out that the recipe for a chocolate cake is mathematically identical to the architectural blueprint for the Empire State Building.
That is deeply unsettling, honestly, but also kind of amazing. The underlying code of the universe just repeated itself in two entirely different domains.
And it did it again in what mathematicians call monstrous moonshine.
Monstrous moonshine.
Yeah, discovered between 1978 and 1998. Researchers found an exact connection bridging finite group theory and modular forms.
Let's do another quick translation for the listener. What are finite groups and modular forms?
Sure. So finite group theory is the study of symmetry. Imagine rotating a 3D cube. There are only so many ways you can turn it where it still looks identical. Mathematicians discovered a theoretical shape with the highest possible level of symmetry, existing in 196,883 dimensions. Right. They call it the monster group. Modular forms, on the other hand, are highly complex, symmetrical functions graphed on a two-dimensional complex plane. They belong to a totally different branch of math.
So we have a theoretical shape in 196,883 dimensions and a 2D graphing function. Where is the bridge?
A mathematician noticed that a specific, crucial coefficient in the 2D modular form was the number 196,884, which is exactly the dimension of the monster group, 196,883 plus 1.
A difference of 1. Come on.
And it wasn't a coincidence. This bizarre +1 correspondence systematically carried on across an infinite series of numbers between the two fields.
Okay, these unreasonable connections are blowing my mind. But let me push back on behalf of everyone listening.
Go for it.
With Ulam's spiral, the prime diagonals are just there. With monstrous moonshine, the +1 connection is just there. These are unavoidable patterns. You don't have to search for them. They just fall out of the math. But if we are looking for a message in pi, what constitutes an unavoidable pattern? If we aren't looking for a picture of a circle, what should we actually be looking for that can't be dismissed as a coincidence?
If we connect this to the bigger picture, the source text offers a brilliant answer. The most non-arbitrary, undeniable target to look for in pi isn't a circle or the word hello. The ultimate target is Gödelian self-reference.
Gödelian self-reference. Okay, we need to build a mental model for that. How does that work?
Well, in 1931, the logician Kurt Gödel published his incompleteness theorems. He basically broke mathematics by proving that in any sufficiently powerful, formal mathematical system, there are statements that assert their own unprovability.
Oh, like the classic paradox. This statement is false.
Again,
If it's true, it's false. If it's false, it's true. It's a logical loop that breaks your brain.
exactly like that, but Gödel did it with rigorous, unarguable mathematics.
Mm.
He invented something called Gödel numbering. He created a system where every mathematical symbol like plus, minus, or equals was assigned a specific prime number.
Oh, clever.
Yeah, and by multiplying these together, an entire complex mathematical sentence could be translated into one massive, unique number.
So the math can suddenly perform calculations on its own logical statements. It's like math talking about math.
Yes, the system becomes self-referential. You can write an equation that mathematically translates to. This specific equation cannot be proven.
Okay, I'm with you.
Now, here is the revelation about pi. Remember the BBP formula we talked about earlier?
Yeah.
The teleporter.
Yeah.
It is already self-referential.
Wait, how is a formula for pi talking about itself?
BBP encodes pi's hexadecimal digits using a base 16 sum where the denominators and coefficients are fixed by the underlying structure of pi itself. The formula relies on the mathematical DNA of pi to extract the digits of pi.
So it's a loop.
Exactly. The tool isn't separate from the object it's observing. It is fundamentally intertwined with it.
Let me see if I have this straight. I do see a vulnerability here, though.
What's it?
Isn't looking specifically in base 16 just because of the BBP formula, or looking in base 10 just because of the Rabinowitz-Spigot algorithm? Isn't that just another form of cherry picking?
How do you mean?
Like, if I take a pattern found in base 16 and translate it back to our normal base 10, the pattern completely disappears. It looks like random static again.
Doesn't that mean we're just arbitrarily choosing whatever base gives us the coolest answer?
That is a very sharp observation, and it's the exact objection skeptics would raise. But the author's rebuttal is that the base isn't just arbitrary decorative packaging, it is constitutive of the discovery mechanism.
Constitutive, meaning it's baked into the physical reality of the tool itself.
Precisely. You can't separate Ulam's prime diagonals from the geometry of the spiral. The lines don't exist without the spiral. You can't separate the BBP formula's teleporter power from base 16 arithmetic.
Because that's the only way the teleporter works. Right. The math only allows you to skip digits because of how base 16 interacts with modular arithmetic. And with the Rabinowitz-Wagon algorithm, it natively outputs base 10 digits by structural design. Base 10 isn't just cherry-picked, it's our default human symbolic system, and the algorithm mechanically drips in that exact base.
So the base isn't arbitrary?
No. The structure is representation dependent, and that's not a flaw, it's a feature of the universe.
Okay, so the base is the lens of the telescope. You can't complain that a radio telescope doesn't show you optical light. It's doing exactly what its structural physics demands.
Which brings us to the ultimate climax of the dissertation, the triangulation framework.
The triangulation framework sounds intense.
It is. This is how you completely, definitively collapse the Texas sharpshooter fallacy. You overdetermine the target by combining all three constraints we just talked about.
Okay, so if BBP is the teleporter, and Rabinowitz is the conveyor belt, and Gödelian self-reference is the target, how does mashing them together prove anything? Like, why do we even need the conveyor belt if the teleporter is so powerful? Doesn't BBP make the spigot obsolete?
Not at all. They serve completely different complementary purposes.
Huh.
Think of it as a three-point verification system. Constraint 1 is the BBP formula. It gives you targeted, self-referential access in base 16. You have your GPS coordinates to test a specific spot without endlessly scanning.
All right, constraint 1. Got it.
Constraint 2 is the Rabinowitz-Wagon algorithm. It provides mechanical, sequential, base 10 output. It forces sequential revelation. You need it because you can't cheat it. It proves the pattern exists naturally in our human numeric base without skipping around.
And constraint 3.
Constraint 3 is Gödel. The target we are looking for isn't an arbitrary drawing of a circle. The target is a mathematical statement embedded in the digits that talks about its own structure.
So if I'm understanding this, if you search for logical self-reference using a self-referential algorithm inside the only mathematical constant known to support such an extraction, you aren't painting the target after the shot.
No, because the pattern type, the access mechanism, and the mathematical constant itself are all structurally identical. They share the same underlying mathematical DNA.
It's like finding a keyhole in a completely alien landscape. You look at it, and it perfectly matches the shape of a key you already have in your pocket. And then when you slide the key in, it perfectly engages the microscopic tumblers inside the lock.
That's a beautiful analogy.
You didn't invent the lock, and you didn't invent the key. The universe provided both, entirely independently, and yet they only work when brought together. That implies profound design, not a random cloud shaped like a dog.
Exactly. The epistemology of design detection here completely bypasses statistical probability. We don't have to argue about the odds of finding a sequence of ones and zeros. It relies on structural identity. Discovery without pre-specification becomes possible because the specification is built into the mathematics itself.
This has been a massive, mind-expanding journey. We started with a sci-fi thought experiment about aliens leaving a picture of a circle on the digits of pi, and we've moved to a profound realization about reality itself.
Which is pretty cool for a deep dive on math.
Yeah. The way we mathematically observe the universe actually dictates what truths we can uncover, whether it's Ulam's spiral doodles revealing the secret machinery of prime numbers, or Dyson mapping quantum physics onto number theory. The instrument creates the visibility.
It really forces us to step back and ask not just what is out there in the cosmos, but what our current tools are actually capable of showing us.
Which leaves me with one final, incredibly provocative thought for you to chew on today. We just learned that our mathematical tools, like the BBP formula or Ulam's spiral act, as observatories that dictate the structures we can see.
Right.
So what massive, universe-altering structures are sitting right in front of us right now, completely invisible, simply because we haven't invented the right coordinate system or the right spiral to look through yet? The message might already be there, hiding in plain sight, just waiting for us to build the right telescope to see it.